So we just started talking a bit about fields. A field is a commutative ring with identity, where every non-zero element actually has an inverse. So there's other ways you can think about this. It's a commutative ring with identity, where if you remove zero, you have a group under multiplication. Or you can think of the field as a commutative ring with identity where zero is maximal ideal. Now, if you have a field, what can the characteristic of the field be? Anybody remember what the characteristic of a ring is? What are my choices for a field? It can be characteristic zero. That means that one has infinite order additively, in which case F contains an isomorphic copy of Q. Must be, right? Because if you characteristic zero, you contain all the integers. And now if you're a field, you have to be able to invert all non-zero integers. And so your field has to contain Q. If it's not zero, what's the characteristic of the field have to be? It has to be prime. And in this case, the field must contain an isomorphic copy of the integers modulo p. And in fact, this one's even easier because what happens additively is if you're, in fact, if you have any ring that has characteristic p, it must contain CP. Because the one will additively generate everything.
Last one more time. What does the characteristic Z?
So let me. Yeah. And yeah, no such thing exists. We say characteristic are zero. Equivalently, one has infinite order. There. You can generalize the notion of characteristic for rings without identity. And basically what it means to be characteristic n is it's the smallest n such that anything added to itself n times zero. And if no such n exists, we say it's characteristic zero. Okay. Right. Definition. A field is said to be an extension field of F. The field K is an extension field of F. And sometimes I'll just be lazy and say it's an extension of that. If F is containing K. Okay, right, easy peasy lemon squeezy. What does it mean to be an extension field? It's just a bigger field containing F. That's it. And sometimes we say, let me point out that F is contained in K, right? K is an F module, right? Because basically add two elements of K, it's still an element of K. When you multiply by the scalar from F, it's still in K. So F is a field, so K is a vector space. Vector space over F. And we say 3, 2, out. And we'll write this way. But we said the dimension of K over F. This is the notation. I've also the degree of K over F as a field extension. And whenever we say this, we mean as a vector space. And if we have a field E, the F with E between F and K, we say that D is an intermediate field extension. Intermediate between F and K. If I say intermediate extension, I get hopefully two contacts. Okay, so here is the first important result, and this rears its head over and over again. Theorem 813. Then degree dimension is multiplicative. So K is big vector space over F. That is the degree of that is dimension of K over E is vector space times dimension of field. F is vector space. And this is true even in the case where this is not finite. Right, so and this is for the proof. Proof. So I am going to call you the basis for E over F, and I'll call B. Uh, show. Well, anybody want to take a stab at what we should probably think about showing here? Here's wildest wishes. I'll say something like this. Okay, my first task is I want to show that this set, when I take doing willy-nilly multiplication, where willy-nilly means every possible UI comes to J, that this set X, this new set that I've constructed, actually gives me a basis for K over X. So how do we do this? Well, I don't know much, but this is a basis for K over E. So I'm gonna go down to the intermediate thing here. So I know that K is equal to now, yes, I realize that this index is very big, but I'll just re-index whatever elements I need, setting myself in the representation. The important thing here is that this K can be written as a finite sum of, that is a finite linear combination of these E's. So where do you suppose my next step is going to be here? Yeah.
Expand the e's because U is a basis for E over F.
Good. Again, you might get upset with me because they're in these EIs. So how do I know they all end up with U? But remember, I can make as many of these term zeros as I want. So I can just sort of take the union of all the UIs that are needed to generate the TIs. Use that way. Everybody okay with that? So in particular, K is equal to A11 U1 plus A1M UM B1 plus A N one U1 plus A N2 U2 plus A N M UM times B. And notice that K were the AIs. The AIs
The last one should be A I. E I.
Oh, no, this is the last term. This is,
Yeah.
right.
No, that's A I.
In your EI, you wrote EI instead of AI.
Oh, my bad, okay. Is that what you meant? Yeah, yeah. So, I don't even see it. So K is a linear combination of set EI, EJ. Okay, I'm sorry, yeah. There's always AIJ from there. So in particular, the set X spans. A over F. Now we just have to show that it's linearly independent, and we're going to stair step on this one. So the second thing we need to do to show this is basis is we need to show it's linearly independent. Well, let us suppose that we have some is equal to 0. So here Fij is in basis. So 0 is the sum over J, sum so rewriting the sum this way, notice this internal thing, every one of these sums of Fij ui, the F's are in F and the Ui's are in E. So this is a finite linear combination of these things. So for all J, sum Fij ui is 0. Because B is linearly independent over right. So notice that every one of these coefficients out of E has to be 0 because you have a linear combination of the sum of the J's 0. That means all the coefficients have to be 0. Right? But now we take it a step down further. UI is 0 and UI set U is linearly independent over F. This means each Fij is equal to 0. And that's exactly what we want to do. Therefore, X is linearly independent over X's basis for K over F. And so all that remains is to count. But notice the K, it's the K X. So cardinality of X, cardinality of X, okay? That's essentially my index set. It's cardinality of Y, cardinality of J. And this correctly means that the degree of F over K is, well, technically the I is any questions? Okay, so let me talk you through some terminology here. So X, well, let me say if X is equal. And X, you have the subset. And subfield of F generated by X. Subfield, some field generated by X. This is the intersection of all fields that contain, all subfields that contain X. This can be construed as the smallest field that contains X. And I'll show you sort of the practical way that we think about this. So in the case, and we're going to be dealing with this case a lot, with the case where X is in fact in the case where X is finite, or in fact sometimes just a single element. Oh, by the way, let me ask you this. What is this? What is this in the case that X is the empty set? Because if you think about it, was it?
It'd be 0.
Yeah, it depends on your definitions, I guess. I would say that I want a field to contain an identity element that is not 0. Think about the empty set. What characteristic should this have? My answer depends. Well, if X were the entirety of that, and it might not have to be this, it would be something true, but we're gonna look at the intersection of all the subfields. There's actually two answers. It depends on what the characteristic is. What if the characteristic is 0? It should be the intersection of all fields contained inside. Right? And if the characteristic is 0, every field will contain Q. So if the Q in characteristic is 0, and the characteristic of P, it should be CP. But your answer was correct if you want to construe 0 as a field. But we won't, I'm not gonna do that. I'm gonna construe any field as having to be at least the rationals or at least CP. Yeah. That's fine. A1, A2, N. And K inside out is a subfield. Then this notation is the smallest ring, actually, that's the ring, containing K and known as A1, A2. This is super sloppy, but I think this is sort of polynomials in A1, A2, and A-N. This isn't completely true because these polynomials may have a relation on them, or may have many relations on them, right? But you can obtain this field by looking at K x1, x2 up to xn and modding out by the ideal of x minus a1, x minus a2. This is the smallest ring containing K and these elements. This is, and I'll put it like this. This is the set. Right, so here's kind of computation layer. What does a typical element of this look like? Take any polynomial and n variables in the polynomial range of n variables here, and plug in A1, A2 up to A. That's what a typical element of this looks like. This is the smallest field. Okay. A1, A2. Anybody want to hazard a guess what this looks like? No, actually, that's too big. Yeah. So this is actually where you're back to see. And of course, boy, something like this. So a typical element of the smallest field containing K are rational functions in A1 and A. So take your favorite P of X over Q of X and plug this in willy-nilly, as long as the denominator is not the same. So this is the smallest. This is the smallest ring you get, right? And this is the smallest field where you make sure that everything there is invertible. You know, X is one element, then KA is called a simple extension. So just one variable needed to do the computations. And finally, if L and M and F are subfields, the composite which is LM is subfield of F generated by L U M. So the composite of two subfields of F is just a small subfield of F that contains both fields, contains both as individual entities, if you will. Let me give you an example. Um, Smallest ring that contains Q and square root. So a typical element of this might look like something like this. We'll find out. What's a typical element of this look like? It's the smallest ring that contains Q and radical 2. So I can get an element by taking an arbitrary polynomial in QX and plugging in radical 2. Let's see what we get. Three times 2 radical 2. We'll say 4 times 4. A n 2 n over 2. I agree with that. We can clean this up quite a bit. Does anybody see how? Notice that all the even terms are rational numbers. And all the ones that came out of the algebraic, it's a rational number times radical two. So I could, at the end of the day, write it that way. Everybody agree with that? That's kind of. What about this? Oh, yucky yuck. Now I've got all rational functions. But I already know that every element of this ring is this form. So so if I did the rational functions, I did simplification. Where A, B, C, D, rationals, and I need C plus D by two, not be zero. And actually, to prevent this, all I have to do is make sure that both C and D can't both be zero. But let's go a step further. What can I do with this? I know, I feel like I'm back in like some mindless algebra two class in high school where some ancient person comes up to me and says, rationalize the denominator, right? And so, believe it or not, it was important. Although the ancient person, but I didn't know why. I can certainly do that. Whatever. And this becomes C squared minus two D squared. Now, again, you need to convince yourself that this is not zero, but of course, if this were zero, one of these two has to be zero. I know this is not zero. And notice, well, convince yourself of this. If this is zero and this is zero, then we'll have a problem. Look at what happens up top. We have AC minus two BD plus BC minus AD radical two. Very good. And I can write this as AC minus two BD over C squared minus two D squared. BC minus AD over C squared minus two D squared, two D squared. Right. Somebody smell what rock's cooking here. What does this mean? What I've shown is an arbitrary element of Q round bracket right to be written as rational plus a rational times radical two. So a typical element of this lives here, clearly the other containment holes, so these two are actually the same. Does anybody want to put their finger on what it is that actually made this work? Why is this the case that these are the same?
Was this to some part of this version?
That's right, because I could do this collapse here, that was really the machine behind what made this work. And we're gonna see in general, that this happens more generally, not just because you can square this to radical two. This happens for so-called any algebraic element. Which I find present. But first, let me give you, let me do another piece of example. Here's another field extension. Here, I'm just not even going to fool around. I'm going to take QX. This is just polynomials over, this is the smallest ring that contains the rational numbers and the variable X, right? This is the smallest thing you can form. You have to have all linear combinations over Q of powers of X, that's it. These are rational functions in X. Notice that it's pretty clear, isn't it, that this one's bigger, because, for example, 1 over X is in here, and 1 over X is not a polynomial. So this one, contrasting with this, is quite different. And if you think that I'm putting a variable instead of a number, this is also true, and by E here, I mean, like I'm sitting in math 10, I mean, the natural place in water. Definition. Let K and F. Melton, a bigger field. We say that U is algebraic over K. If U is a root of a non-zero, I want to be non-zero, it's a zero polynomial. If U is not algebraic, you say that U is transcendental. Okay. You say U is transcendental. If every element of F is algebraic over K, we say that F is an algebraic extension. You say F. Right? Yeah, there exists a transcendental. There is this element in F transcendental over K. We say F over K. So algebraic is algebraic is reserved for only the best. An algebraic element, extension means that every single element in F is algebraic, over the base field. If there's even one transcendental element, we can say it is, transcendental. So here's some examples. Okay, let's start with the smart element example. If you walk up to me on the street, you give me a field F, I can automatically give you an algebraic extension of F. What is that? So, pretty glad. Any field is algebraic over itself. U and F is a root of X minus U. So in a very silly way, any field is algebraic over itself. Q radical 2 is algebraic over Q. We've already figured out that a typical element looks like this. Our previous example, we showed that a typical element of Q radical 2 is like that. Here, of course, A of theta Q. This is a root of this quadratic formula. You can see that this element is root this, so every element in Q radical 2 is a root of there's a polynomial. R is transcendental. Will be two. Somebody tell me why you know this one. Should be as easy as pi. How many of you are aware of the pi meaning, for example, transcendental number? Right? Well, what if you couldn't give you that specific example? Anybody give another argument, maybe a size argument of why this has to be the case? How many polynomials are there over Q? Countably many or uncountable? Countably many, right? The constants, the linears, whatever. Countable union, countable sets is countable. So how many complex numbers can be algebraic? There's only countably many polynomials, each of which only has finite many roots. There can only be countably many algebraic numbers. Do I agree with it? How big's the reals? It's uncountable. In fact, in a certain sense, most reals are transcendental. But C is algebraic over wrinkles. If X is pi, X is a polynomial variable, then KX is transcendental. Okay. Because this X does not satisfy a polynomial equation. Okay, any questions on that? It's a good place to stop for the day. I will, if there are any questions, I will see you all next time.